Noted. Okay, let's try an example. Example 1. We have a conductor. The current in the conductor is 6.4 amperes. We know that we will have an electron flow, right? In the opposite direction. We have to find the number of free electron flow in 5 seconds. So we know that I is equal so I is equal Q over T. But Q, that is not directly the electrons. If you can remember what we studied in electric field, Q is N times E. So that is NE over T. We have to find N. So N is equal IT over E. So there is 4 times. 20 2 into 10 to the power 18. So this N, it doesn't have any units. It's just a number. See if you got this answer. Saja, how about you? Have you got that same answer? Example 2. We have a ring that is charged with charge Q. It is rotated with a speed of omega. Here the charge is Q. We have to find the current I. Find I. We know that I is the rate of flow of charge. Now, if we rotate a charged ring, It is also just like the charges are moving. Therefore, we can consider that as current. Okay. So to find the current I, let's think about the units. What is the unit of current? That is Coulomb per second. So here we have Coulomb, but omega is radian per second. What is per second? Here we have Coulomb. Then if I find something with per second, if I multiply them, then I should get the current. So what is per second? That's the frequency, right? So from omega, we have to find the frequency. And from frequency, if we substitute into the equation, we should get the current I. So I is equal Q into F, because it is Coulomb, this is per second. But omega is 2 pi F, then F is omega over 2 pi. Just replace F. So I is equal Q omega over 2 pi. Got it? Okay, so next topic is drift velocity. So what is drift velocity? The velocity of electrons of an electric current flowing through a conductor is known as the drift velocity. Now we have we have a lot of cations. When we have these cations, electrons cannot move directly. It has to bounce off these cations and move to the other end. So here, this is the net displacement. This will be the net displacement. net displacement. D. So drift velocity is equal to D over T. Got it? We have cations. Because of these cations, these electrons, they cannot move directly. They collide and bounce off, and this is how they move. So drift velocity is a mean velocity. So when we find the mean velocity, we find the net displacement between these 2 points and the time taken, and that will give us the drift velocity. Let's say length of this conductor is L. Length of this conductor is L, and cross-sectional area of this is A. So I'll mention, consider length L of a conductor. The number of charge carriers, the number of charge carrier in volume AL, that is equal NAL. How this is volume? L is length, A is area. When you multiply, you get this whole volume. What is this N? N is the number of charge carrier per unit volume. So when you multiply volume and number per unit volume, you get the number in that certain volume. So what is the charge? Charge contained in the volume. Now what we have found is number. So it's just like Q is equal to NE. We have only found N, that is NAL. If we multiply that by E, then only we would be getting the charge. So how to get the charge? Multiply by E. So that is NALE. NALE. But we know that I is equal to Q over T. Instead of Q, I can use this NALE over T. So what is L over T? L is the net displacement. L is the net displacement. T is the time taken. So instead of L over T, instead of this, we can take, we can consider it as the drift velocity. NAVDE. So we come to the equation E is equal NEVDA. VD is subscript. So just look, I never forget this equation, just an R missing. So you won't be forgetting this equation. You can always remember. So here, what is N? N is the number of charge carrier number of charge carrier per unit volume. Per unit volume. E is the charge of an electron. Charge of an electron. And then we have Vd, that's the drift velocity. That's the drift velocity. A is the cross-sectional area. Cross-sectional area. Noted. Just look this L over T. Now, just when I say length over time is drift velocity, we are not able to accept it, right? So this is how it works. Just look. Now in this volume, we have n number of electrons, sorry, n number of charges. We have, in this volume, we have n number of charges totally, okay? And here we have the last charge. So I'll take it as E. So when this last charge comes over here, how much of charge has gone out of this volume? That is N. So how much distance did this travel? This last electron traveled a distance of L. So what is the time taken? That is T. Then at what rate did the charges leave this surface? Leave this volume. That is also at the same time T. How much? N E. N into that certain amount of Q. So both the time taken by all these charges to leave this surface, sorry, not the surface, this volume, and the time taken by the last electron from here to reach here are same. That is why I was able to relate L over T to Vd and also this current Q by T. Is that idea clear? Both of you, Saja, are you okay? You got it? How I related Q by T and this L over T. Noted up to this, right? So let's try an example. Sorry, note number 1. When a charge is placed in an electric field, it always accelerates. It always accelerates. Therefore, a charge cannot move in a constant speed inside a conductor. Okay, so did you get it? Vd is not constant. It always accelerates. Then during a collision, it loses the energy and its velocity goes down. Again, it collides. Again, it accelerates due to the electric field. So it continues. So let's say the electric field is applied in this direction. Then the negative charge will move in this direction. It collides. It collides with a cation. When it collides with a cation, again, the velocity will start from a lower level. And when it increases up to a certain level, again, it might collide. Again, it might collide with another cation. So what happens here? The free electron, the free electron gains kinetic energy due to the electric field, but loses it loses it in collision with cations. Hence, hence the speed hence the speed is not uniform. Okay, hence the speed is not uniform. Therefore, we consider mean of the drift velocity. We consider a mean drift velocity. That means the average drift velocity. Up to this, is the idea clear? Sarah, clear? Okay, note number 2. Just look at this equation. In this equation, let's consider a given material. In that given material or given conductor, what are constants? N, that depends upon the material. So if you're using the same material, it is constant. E is the charge of an electron. It is constant. Area of the conductor, it is also constant. Then current depends on drift velocity. So if I change current, what changes? The drift velocity changes. Others remain constant. Okay. So we can say that when magnitude of current, when magnitude of current is increased, the drift velocity, the drift velocity Vd is the only variable, is the only variable, is the only variable for a given conductor. Other factors remain constant. A copper conductor, of cross-sectional area 2 millimeter square carries a current of 4.8 amperes. N is 8.4 into 10 to the 28 per meter cube. And E is 1.6 into 10 to the minus 19 coulomb. Find Vd. Find Vd. Can you? Millimeter square, 8. 6. These two together, it's 25. Minus 3, 10 to the minus 3. Zero 0.179. So look how small the speed is. Okay. Saja, how about you? Clear so far? So next we have current density. Current density. So current density, if you just know what is current density, that's enough. The current flowing through unit area of cross section, unit area of cross section of a conductor, of a current carrying conductor, of a current carrying conductor is the current density. Is the current density. So the equation is J is equal I divided by A. But we know that J is equal I over A. Instead of I, we have NEVDA over A. So just cancel off those area. Now we have a new equation for J. J is equal NEVD. So under electricity, we won't be using this current density anywhere. You only just want to know what is current density. You will understand in a minute why we need to know about current density. not number 1. We know that J is equal I over A. I is amperes and this is meter square. Therefore, J is ampere meter minus 2. Second, do you have an idea about macroscopic properties? Macroscopic quantity and microscopic quantity. What do we understand by macroscopic quantity? At least one of the quantity is observable with our naked eye. But microscopic is not like that. So for macroscopic quantity, we can say temperature, pressure, density, all of these are macroscopic. Microscopic, all of them are at microscopic level. You will need to go to the microscopic level to understand that. So with this idea, just look at the equation. Just look at the equation for current density. So in current density, N, that is the number of charge carriers in a unit volume. Then we have charge of an electron. Next, we have drift velocity of a charge carrier. So this N and Vd are at microscopic level. So what can you tell about J? Current density is a microscopic quantity. Got that idea? You understand why this is a microscopic quantity. But what about current? Is current a microscopic quantity? Is current microscopic? No, because we have area. Area is a macroscopic property. You can measure it. So current is also measurable. Okay, Sarah. Here,